There we are. Right.
Hello, I've got a special treat for you today because I'm joined by Jez, who on your online presence sometimes describes yourself as a software granddad. Is that right?
Yes, it is, yes.
So welcome, Jez. We're going to do, this is like a one-off thing that we're going to do. So why don't you tell us what you're doing?
What am I doing? Okay, the software granddad thing came from when I was trying to pitch myself a little bit more, not exactly as a coach, but as a kind of, you can see the grey here, Andy, you know, as somebody who could look after the kids while also taking them on an adventure, right? That's what I was.
Yeah, perfect.
That's what I was trying to do. So, as you know, I've had this long running thing in C++ that I've been doing for several years, and I finished that at the start of the year. I went through software tools in Pascal and wrote all the programs in that in another language. Right, and I've been kind of casting around for something else to do for fun, right?
Fun stuff to do.
Fun stuff to do.
By the way, I'll put a link to your Mastodon or something in the video so that people can find.
Lovely.
They can catch up on all of your adventures.
So, you, of course, have been working away. You did all those videos on Rust, on learning Rust, and you've been working away on Milk for like a dervish, frankly, Andy. I'm several behind, but I'm doing my best to catch up. And so I thought,
and you described yourself as watching my videos sometimes and saying, Andy.
Well, yes, like yes. As well, you know, I'm worried about your commit frequency, Andy.
That's bad.
And you know, anyway, let's not go down that. So I thought, well, you know, I've got this lovely. I pay all this money to JetBrains for their lovely tools. I've got this Rust rover. There must be something I can do in Rust. And I thought about maybe just seeing if I could send you a patch for Milk or something, but that seemed a little bit rude because that's your thing that you're working on. And if somebody else from the past who's like behind you starts sending you PRs, that'll disrupt the flow of what you're doing there. But then I remembered Cell, which was a project of yours from 10 years ago, maybe?
I guess. Is it really?
10 years ago. Where you wrote this little Lisp-like language. I mean, it is a Lisp, but you just put a couple of extra bits of syntax in so that people wouldn't go, oh, that's a Lisp, and turn off. Right? Which is a remarkable bit of work. And you wrote it in Python, which was and did that lovely talk on it at ACU. And then it was about 4 years ago, I was doing a talk. We were all shut in our houses, and I was doing a talk for our friends over at Nordev, and I was going to do something about basically what compilers do, what interpreters do. This is our code, but how does that turn into the computer actually doing something? And I thought, I need a little language for this. JavaScript's a bit too complicated, but then I could do, there's Cell. And I re-implemented Cell.
And I cannot describe how excited I was when this happened.
I nearly wore my Rabbit Escape t-shirt this evening, Andy. But it was great. And the way I did it was I took your tests and I crossed out the colons and I put in some curly brackets and turned them into, I'm not even sure what I'm using, Jest, I think. Anyway, turned them into unit tests in JavaScript and then implemented the code to make those tests pass. So I didn't refer to your implementation. I just use your tests.
It's very interesting. And by the way, right? You told me this before, but I hadn't thought of this before. So did you have the full suite of tests in front of you when you started implementing?
No. Well, kind of. So I knew what all the tests were, but I took them kind of in a little, like one at a time. Or
okay, good. Because I think, because I obviously wrote the code with, like in a very test-driven way, with just getting one test to pass at a time. If you had just taken that whole suite of tests and made them pass all in one go, that would have been very different. Okay.
No. So the first one is, Lexing an empty string produces nothing. Right. So that's where I started with that. And then the next one is we Lex the next thing. And then there are some that go in a little group, like, all the arithmetic operators. But basically I did them kind of one by one, top to bottom. Because that's how they get more. And then I did some other stuff with it. I did some constant folding as a post process, and I did to show what you could do with the AST, and I did some obfuscation, and I almost did some tree shaking.
Wow!
And that was really good fun. So I thought, well, I'll do that I could do that again. I'll do it again. I'll take my JavaScript tests, and I'll take them into Rust. And then I'll implement it in Rust. Because, of course, the idea of Cell was you didn't need a lot of code to implement it.
Yeah, that's the main point of Cell. If people haven't seen Cell, it's a language designed to be a short implementation for the person implementing the language.
Yes.
As opposed to for the person writing code in the language, which can be different.
It was quite lengthy. So if I whip across, actually, if I just whip across here, and hang on. I go into lib and we have a look there. If we clock that, we've got 500 lines or so. 500, 600
That's
lines.
pretty impressive. How does that compare with the Python? Do you remember?
I don't know. It's similar. It's really really quite similar. So it's just, it's just a few. So it really is quite small, and it's quite because you can be quite relaxed about your types in Python and JavaScript. They are typed, but they're quite relaxed about it. There are a lot of kind of tuples, or what you might think of as like a tagged tuple. So we've got a string. And then you might, because it's that, I'm looking for two more tuples, or I'm looking for whatever. So we're quite relaxed about the typing. We're just building up these arbitrary arrays, nested arrays, basically.
That's the worst thing about the implement. If I remember, I don't remember it that well, but the worst thing about Cell's implementation in Python is that I decided that classes were too much typing, and I was just going to use tuples, and it's painful.
In JavaScript, that's surprisingly natural, right?
Right, yeah.
But we have to. So as I brought it across into Rust, and here is and it's very modular. So you've got a Lexer and a parser, and then an evaluator. And basically, in I can't remember if you did this in Python or not, but certainly in JavaScript, I wrote the Lexer and the parser both as generators. So they're just iterating, and they give you the next token in the Lexer case, and then the next
I'm pretty
AST
sure.
node.
Pretty sure they're iterators in Python.
So that's what I have in my Rust. So here's
tell us how much Rust you've done then. Is this your first ever Rust?
No, I have done a tiny bit a few years ago. So I was then working on a networking library, cross-platform, a multi-implementation networking library. It's not a cross-platform, it's multi-implementation. So there were several implementations in different languages.
Right. Okay.
And I was working on one written in Kotlin. And there was some existing code that I was contracted to extend. And there was I think a Go version, and there was a Rust version, and there might have been another one that I've forgotten. And as far as I can tell, because these were kind of different open source. It was all open source stuff, and it was and I don't quite know who's working on when, and some of them were in different time zones, and some of them were difficult to deal with. I think that I was the first person to try to get these different implementations to talk to each other.
Right. Okay.
Consequently, of course,
they didn't work.
Found some problems. And so I did do a little bit of work in Go, and I did do a little bit of work in Rust. But most of what I remember I'm looking at it, recalling it now, I don't think it was really great Rust, actually. And most of what I was doing seemed to be adding unwrap.
Right. I mean, a few years ago, Rust, like idiomatic Rust, did look
sometimes
different.
Sometimes twice. Yeah.
Oh, yeah, you've got to do a lot of unwrap. Yeah, a few years ago, like idiomatic Rust did look a bit different, so it might be that some of the stuff you can do now you couldn't do then. But yeah.
Right. And so I've I'd done that, but I hadn't really started with nothing. And so my recent knowledge is largely gained from watching your late night manoeuvrings. But of course, I have this. I am not a NeoVim user. I'm not an IDE power user, but I have this lovely Rust rope in front of me, and so you can kind of start typing, and it'll feed you bits.
Right.
So I have done the Lexer.
Okay.
And obviously it's changed a lot from where I started, but I don't think we need to go through the whole history of that. But I think what I have here is not bad, but there are bits of it I don't understand. Right. So I get this public function, Lex. So this is a function, and it's callable from outside this module. And it's taking here a reference to a str, which is like a slice. It's like a character array, right?
It's
not a string.
You don't own it, but you are guaranteed that it's a set of contiguous bytes which are UTF-8, and you know the start and the length.
Right. And this is my return type, which is a Lexer.
Yes, which is particularly confusing.
Yes,
this pattern
which is
of iterators that have to have their own. There's their own structure, which are iterable. Which I guess is what you're doing here. Is that right?
Yes, exactly. Yes. So that's fine, because I'm absolutely okay with iteration, right? And it's kind of what I was expecting. But
you've got that little tick underscore there, which we can just ignore.
Right. Well, this is the thing, because I was working away, and at some point it said, you need to do a lifetime something or other. And I went, do I? It said, do you want me to put it in? And I said, yeah. and it did this. Yeah.
So we can talk about that if you like.
Yeah. And then the whole thing lit up like a Christmas tree, and I had to put it in lots of other places.
Yeah.
I assume this is a wildcard thing, this underscore.
Yes.
Right. Yeah. So the dash here is a lifetime, saying this is a lifetime.
Yep.
And the underscore here is a wildcard that's saying we don't care about the lifetime here because it'll happen at the other end.
Yeah, it's basically saying there is a lifetime here, and I don't need to name it. So can you just whatever, it exists.
And I've named it here.
Yes.
So this is where I declare my class effectively. But here I'm just giving the data members.
Yes.
And I have to name the lifetime here because I have to specify that the lifetime of this and the lifetime of this thing are the same.
Well, yeah. So the point is, when you take in input, you've got a reference to something, and so anyone who gets that Lexer back by calling the Lex function needs to know how long the Lexer is allowed to live before it starts referring to some invalid memory or something. So in this case, you're passing in that str and you're then returning something.
So it's the other way around. It's saying this Lexer, the lifetime of the Lexer is tied to the lifetime of the characters.
Exactly. And we could probably make it more explicit. You might be allowed, if I'm understanding it right, which I might not be, but if I'm understanding it right, you might be able to say, in your Lex function, you could put diagonal brackets tick A, like after the word Lex, and then put that lifetime on the reference and the return value. And then like because I think this Lexer is tied to the lifetime of that str that's being passed in.
Right.
But the reason why the struct Lexer has to have a lifetime, like the approximate reason, is because the chars thing that you're using has to have a lifetime, and that's because chars is like giving you the characters of some other thing that it doesn't own, so it has to have it's a reference to.
Right. Yeah. Okay.
So the Lexer kind of inherits that, and now the Lexer is referring to some stuff that it doesn't own, so you need to know how long that underlying thing lives.
Gotcha. And so, right, so my input here, this chars is basically the input stream that I'm working across.
Yeah.
And chars is an iterator over characters.
Yeah. Yeah, it's like an iterator adapter or something. No, actually, no. It's just it just turns a string slice into an iterator. Yes. I guess. Yeah, I guess.
And the iterator in Rust, it has lots of things on it, but the important one is next, which returns an option of the thing.
Yes.
We'll come back to that. And a peakable version of that adds peak.
Right. Yes.
Yes.
Which I had to implement in the Python, but you're getting provided
and
for
in
you.
the job and in JavaScript.
Right.
Yeah. So in my constructor, it's not a constructor, but it's effectively a constructor.
It is a constructor.
Is that right? It is a constructor. Okay. Yes, I'm saying that we set the chars to whatever the input thing is, and we get the char iterator off it, and then we make it peakable. And that's what's going on.
Yeah. So just to do the lifetime thing one more time, right? So when you call chars, you get back an iterator, but it's referring to the stuff in input.
In input, so it has to be So its lifetime can't exceed that of the input.
Exactly.
And then again, the peakable adapter can't exceed the lifetime of the thing it's adapting, which can't exceed the lifetime of the input. Gotcha.
And so, in theory, there could have been this other way of doing it, which is you could have called some. I don't think it exists, but you could have called a method called into chars, which would have given you back an iterator that did own the underlying data.
Right.
And then you wouldn't need the lifetime stuff. Yeah, exactly. Either making a copy or moving, depending. In this case, you'd have to take a copy, but in theory, you could move into it.
Okay. So if we spin down to the tests for a second, and we can see actually how we're using it, and I got quite funky quite quickly in the tests.
This is beyond my macro ability.
I covered it from someone else. So anyway, but basically it means I can do a table like this, and I'm saying this is the name of my test, and that's the input, and what I'm expecting is that thing there, right? So if I give it a left bracket, I expect a left bracket. The token is two strings.
Right.
It's a tuple. That's what this is, right?
Okay.
The round bracket for a tuple, Andy.
Yeah.
And it's going to be a right bracket, and I think, hang on, this is a better one. Look,
yeah, this is easier to do.
It's a symbol with the value A.
So it's a tuple. We're going to just have to fight over tuple or tuple. It's a tuple where the first thing is the type, and the second thing is like if you need some content, it's some content.
Yes, exactly. And I can have and in my table, I've got an array of those. It is an array, isn't it? And then I do some I convert those into a thing. Right. So if we whiz back up here, I say I'm lexing my input, and then I'm collecting it all into a vector. Okay. And then I compare that vector.
And so in theory, you could probably find a way of not doing that collect, but for tests, I find it so much easier to just...
Yes. And there's some magic in the test here, which will do different things depending on what I change this result type, this return type to be.
Yeah, collect...
It's doing some collective magic.
Collect is super magic. Well, I guess it's the compiler that's super magic, but collect is making use of it. Yeah. This is one of the areas of Rust that feels more magic than I would prefer it to be a bit more explicit.
Because if I change this, then it says, oh, well, that's the wrong return type because the return type of this is something else. I don't know what it was, just like vec of option or something. But if I put the result around, it does. Is it like overloading on return type or something?
So...
Does Rust have overloading?
If you just put like a semicolon after this line, it will tell you, I don't know how I don't know what type you've asked for because you haven't told me, because it's ambiguous. So hold on. Do I know? I feel like maybe I just don't know how this works.
But when I put that result thing around it, it magically unwraps the options from the iterator to get the result out, to do the thing, and it if you get an error, it short circuits, right, and returns the error. And if you don't get an error, it unwraps all the options to give you an OK of the vector of the unwrapped things.
Yeah, so you could have returned vec of result, and that would feel natural here because Lex is returning like an iterator of result, right? Is it?
Yes. Yes, the iterator returns an option of a result of the tuple and, in my case, a string.
Well,
next
returns an
weird.
option. Yeah, which is
next
weird. But
returns an option.
Next returns an option, but in a sense, the iterator is over like just the result things.
Yes.
Anyway, okay, we're getting tangled up. But basically, by changing the result type here, you're changing the behavior of the code. So that's interesting. And I think
it's very strange because I started without the result. Yeah. And then when I realised I had to put it in, I think at this stage, all I had to do was change the return type. Yeah. And this thing just carried on going.
That feels weird. So it's a general case. It's a general case of something that Rust can do generally, which is if you declare the type, it uses that to know the type in some other place.
Right. So because there's some kind of I could put some manual type specifier on here.
Yeah. I think you'd need colon
something there or whatever. Yeah, whatever it is. Yeah. Whoops. But because I've declared it here,
that's enough.
This must match it, and so it's picking up that.
Yes.
What do you call it? Do you call it an overload in Rust, or that specialization, or that implementation?
It's doing type inference, and I think it's just inferring the type in some generic.
But you specialize. You can specialize, or no, not specialize. You can implement the traits for particular types, right?
Yeah. So I think what
it's
doing
is selecting that implementation.
Yes, I think it will actually be looking for a type T which implements into result of vec, something like that.
Right.
And then you get this, because you don't get like template specialization like you do in C++, where but instead you can have this into type, which then you can implement that for the different types. So it's doing something like that. But if you ask me to write the code that makes this magic work, I think it would take me a while.
Yeah. No, I understand I understand what's going on in there.
Yeah.
But it's a little bit weird, and I'm lucky, I think, in that this kind of monadic style, not hugely common unless you're, I don't know, like a Haskell weirdo or something. But we have an in-house language where I work, which has support for result, and I think we might call it a maybe. Right. Maybe we don't even name the type. Maybe it's just some and none. I can't remember. Right. which has been the cause of much argument, and which some of us have leaned into quite hard, and others less so.
I find,
and actually, for that, I implemented like a then and an else.
Right. So you're getting that monadic type thing, yeah.
Yes. So if you had a sum, you could chain it with a then. No, sorry, it was a result. If you had an OK, you could chain it with a then, and it would do the right unwrapping to do the thing you want, and then it would wrap it if it needed to.
Yeah,
right. That was these. Whereas we didn't have that before, and you would end up with lots of. You'd end up with a sum and a sum and a sum and a sum.
You end with like curly bracket hell.
Yeah. So it's also quite similar to the promises in JavaScript.
Yeah,
you can chain the promises with then else. So you drop through with the error.
Fortunately, we don't have to do that anymore because we've got proper async syntax in JavaScript. So on this line of code here, like something that would be more common, like this is totally normal and correct code, but you would quite often see let something equal something, and then you would explicitly put the type in the let part
Right.
instead of putting the type on the right-hand side. It's more idiomatic because it just looks neater to declare the type, and then the compiler uses that to know that you meant that there.
Right.
So you're just doing it with the return type instead, but it's the same
Okay.
effect.
And this is because the other thing that took me a little while to pick up is the difference between when you put a semicolon on the end and when you don't.
Yeah, right.
And so is it an expression when it has a... Is everything an expression, but a semicolon is an expression terminator?
I think that if you end it with a semicolon, it's a statement.
Statement. Okay.
If not, it's an expression, but that might be me making up those words. I'm not sure.
Right. But your return is, I don't even know if there's an explicit return because I haven't had to use one. But the return value of a function is the last thing the last expression.
Yeah. And this is one of my favorite things. Like because it's not just the last thing in a function. It's also the last thing in, say, an if or whatever block.
Right. Right.
It's a very neat, like it feels like Lisp. That's why I like it, because it feels like Lisp.
Right. So again, we have this thing in the language at work is similar.
Right.
So we have to leave off the semicolon here so that we actually have an expression that's evaluated.
Yes.
Because if we don't, then there's nothing, and then the return types don't match. Okay.
Yeah,
cool.
And if you put a semicolon in here, it will be unhappy in two ways, because it won't know what to collect into, and it won't have the right return type.
It won't have the right type. Yeah, okay. So,
right.
Okay. So our Lexer is really simple, single pass, forward iterator.
Right. Yeah. Okay. And you've got a very elegant implementation, which you showed me the other day.
Yes. Well, let me just what's that? Oh, that's your code, Andy. Let's get rid of that. Right, hang on. If I drag this over here, maybe this is going to work. Okay. So let's make that a bit bigger. So this is the JavaScript version, and so if we look at the JavaScript Lexer, you'll probably find. There we go. Because this is a generator, we're lexing the input, we make it into a stream, and we loop on the stream. This is very kind of conventional stuff, right? And you go, well, if it's one of these, yield that. And if it looks like that, we collect the rest of it and we yield it, and we yield. And then at the end, if we hit errors, then we throw. So we have an out of band error mechanism. And that caused me some consternation when I realised we didn't have that in Rust. So the equivalent...
Because what we have in Rust is better.
Is different. So this here is the equivalent, is that same function. And it is quite different, I think.
Yes. And you didn't need to do it this way, right? Like, so you could be matching on the result of calling next.
Yes. And I did have that initially. But the matches get progressively more complicated. Or they just start to extend out this way, because like this one here, which I've called self token, which is a really bad name, but for those things which are basically their own tokens, like the brackets,
right.
and like the comma and things, you end up with here is that function. There are 8 of them there, and so everything is disappearing off.
Yeah,
to the side of the screen.
Right, yeah. So you wanted separate functions to do the identification of these different tokens, as opposed to just putting
the identification and the building of the token. Because if we're deciding that the thing returns an option, then if it returns a sum, then it's done it. And if it hasn't, then we need to try the next one.
Right. So which is a really neat way of doing it.
Which is why we've got this here. So we peel off the leading white space. That's easy. We go, right, let's get the next character. And we have a next character. So, and then it's a self token, or I would prefer this just to say or, but there we are. Or it's a symbol, or it's a number, or it's a string, or it's the operation, or it's tab, or it's something else.
Yeah, and this is short-circuiting every time an error pops out, right? So if you return none, then you just try the next thing.
Yes.
But if you return error, then it stops, right?
Yes. No. Yes. Sorry, because these are returning these are returning an option that contains a result.
Right.
This is where it gets confusing.
Right.
If we return, we're always going to get a value out of here. We're always going to get something out of here.
Yeah.
Right. Within this little cascade, we might get an option or a none. And so as soon as if we get a none, we go to the next one, go to the next one, go to the next one. As soon as we get something, as soon as we get some, this evaluation stops. And that sum is returning either a token or an error.
Right.
Because the option is returning a token, but because the token has to be able to signal success or failure,
right,
the token is the result of a token type.
Okay, yeah, I was missing the fact that you had that
yes
type alias.
And that gave me the option, a result inside an option. To me, feels weird.
Yeah,
but once you've decided that the iterator returns an option, that's where you have to go to.
Exactly. So that's very normal in the case of iterators, because option, in a way, maybe option was the wrong choice for iterators. Maybe it should be a different enum called iterating thing.
This is where we had I said we'd had a lot of conversations about this at work, because there was a camp that said, well, some and none are the same as okay and error, and it's just about the context. And then there was a camp that said, well, no, they're the context, because the context is different, we need two different things. And then somewhere in the middle, there's maybe there's a tri-state, right? Yeah. Which is some or none or error.
Yeah. All right. But in this case, I actually think iterators, probably, if I were doing it now, I would have iterators return, there are some more, and here's one, or there are no more, and just have it be a completely separate type from option. Maybe. Because
then you could do the match, because some iterations aren't going to fail, right?
Yeah, exactly. But they are going to stop, probably. So
they are going to stop.
Yeah.
And so if you had its own enum, you could write the appropriate match for it, right? Yeah.
Which we have exactly that. It's just that we're reusing the option enum instead of having one with different names. But I feel like maybe the different names would be good.
Yeah, but it's better than Python, right? Which throws an exception when it hits the end of the iteration, which is that's super weird.
But it's okay because in Python there's no runtime cost to throwing an exception. So
no, okay. So I ended up with this, which I'm quite pleased with.
I mean, it successfully factors your code out in the way you wanted it to factor out. So
yes,
you've got to give you that.
And so I have these. Some of these functions are very simple. And some of them are a little bit more involved. It got quite exciting when I'm trying to pass. I started passing lambdas around. Because, where are we? So I've got this. So if we've got a symbol or a number, they can have obviously more than one character in them. So you need to keep on scanning until you find the end of it. And it's basically the same process, but you've just got a different matcher, right? Yeah. So I have this little build token thing down here. Where are we? Which I was build token.
Yes. Oh, you've done some hard stuff.
I couldn't find a way to name this type, and I didn't know if that was normal.
Yes. So it was a source of great confusion to me for a long time. But yeah, you are not allowed to name a function type like this. What you're actually doing here is a generic. You're introducing a generic parameter without using the normal syntax for it. That's what impl does. So what you're actually saying is that there is a generic parameter f or whatever, and its type is fun chart to option char. And so the compiler at compile time will find the actual type of the function and fill it in, but you're not allowed to. Actually, I might be lying because... Yeah, I think I'm lying because I think what I'm describing is you can't name the type of a closure, but you're not
right.
You're not using closures. You're using functions. So I think you could have. You're using a named function, right?
Yes.
But I think
mainly.
I think there is a syntax for. This,
okay, but if I'd, would that constrain it then to not being right? And so, well, that would be silly.
Yeah. So you're doing the right thing here, which is saying, generate me a version of build token for each type that you encounter, and each time the compiler encounters a closure, it will generate a unique version of this build token.
Right.
Because every lambda has its own unique secret type.
Yes. Okay, yes, and that's quite common, isn't it? I mean, I think C++ is the same there.
Right, yeah, so I find it very confusing, but I now sort of understand it, but it still annoys me. But is that
a compile time thing or a runtime thing then? That's a runtime.
This what you're doing here is compile time polymorphism or whatever, right? This impl blah is like a shortcut way of saying I have a generic parameter with this type.
Okay. Oh, that's interesting. Okay.
So you could have said build token, diagonal brackets, F colon, and then that whole stuff.
Oh, right. Basically,
it's almost exactly. I feel like there's something I read somewhere where it's slightly different, but it's essentially exactly equivalent to that. And what's even more confusing is that if you use impl in other places, it potentially has other meanings. But here, that's
right.
What it is.
Okay. In that case, I think if I'd put that up there, I think that would be more confusing. I think actually having it inline there is more helpful. Okay.
I think it's more readable, but it does obfuscate the fact that it is actually a type parameter that you're...
Right. Okay. So yes. So anyway, that peculiarness of white, I was quite pleased with most of these because they're all quite short.
Yeah.
I was really quite pleased with this one. So while we're building the string token, because that's obviously delimited, you got a opening quote, and then we collect up all the stuff, and then you stop at the end. And I had that. I'd originally written that as a raw loop, and then I thought, oh, hang on a minute, this is a take while, and I put take while in there, and then half my test started failing. And I thought, oh, it's not a take while, because take while consumes the thing that ends the iteration, ends that take. What I need is a take while that leaves the quote on there, because what I need to do is check that when this finishes, that it does have a quote on the end. Right. I haven't just fallen off the end. And then I was thinking, oh, and I looked through, iterate on the iter trait, and it's got 75 of these things. I think it's 76 methods. One of them's next. The rest is all those different takes and drops and all that good stuff, right? And I thought, okay, what I need is I need to peek on it. Can I specialize something on the peekable? And I started to look at how I would implement this. And while I was looking for how I was implementing it, I found that actually it existed.
Yeah, so this is what we talked about the other day. That what they say about the standard library is that it's narrow, as in it doesn't have that many things that are classes, the structures that are part of the standard library, but the ones that are there are very deep. And so there's a load of methods on this stuff.
So the reason that my IDE was not feeding me the name was because I just hadn't imported the right thing. So when I imported...
So did you encounter this thing where you have to bring in a trait and then suddenly you magically get more methods? Yeah.
A little bit. So, but yes, when I added use itertools up the top there, same name as a Python package, of course, with all the extra iterated things. then suddenly I had, where's it gone? I had peakable take while. Where's it gone? There, which does exactly what I want.
Amazing.
And then I had to, I wanted to collect up it a string rather than anything else.
Uh-huh.
And so that's where I've got that type parameter there.
So this is where I was saying it would be slightly more idiomatic to have the colon string after the let instead of putting it there, just because it looks a bit less ugly.
Okay. This, I will say, this is what I was, again, fed by my IDE. But anyway, that was great, because then I've got rid of a loop and I've got rid of a mutating variable, right?
Yeah, although...
So it's very lovely and declarative.
Like, it's nice that you found an algorithm that does this, and that justifies it to me. But, like, I feel like we are often tempted to try and golf doing it this way when actually a loop is clearer and simpler.
No, I would go. I write stuff like this a lot. This is particularly at work. I would write stuff like this a lot. What I would really like is a pipeline operator. But anyway, there we are. So then I had that, and then I had this again. This lovely. I can just check the next, and then or else it. Initially I had an if let mute something, and it just looked like a lot of words. And obviously there is a conditional. There's a conditional here, but there's, I don't know. This felt nicer than the if. And so if we just look gently through here, there are no explicit loops and almost no variables. We've got the one here to capture that so that we can use it in here. And then the only one I've got is this here. Because I need to collect into a string that already has something in it.
Right.
And you can't do that with collect. And so you have to extend it.
Yeah.
There is
iterator,
somewhere you can do something like collect into, and then I could give that token string there, token value. But you need to do something that's something to do with a version, right? It's a collect into is unstable.
Okay. That just means that it's not available effectively. Like, so that means it might be one day. So what you could
that was slightly frustrating. That was all. So you have to create and extend, and that was a little frustrating.
I think what you could do here is you could chain the iterators together. So you could put chur into an iterator of size 1, chain it with peaking take
chain
while,
it to the and then
collect.
No, that would work. That would work.
So you could get rid of another variable.
I could.
So this is lovely. I take your point about, so like, yeah, I think that it's like, if you can express yourself in that streaming style, it's beautiful and it can have other advantages and stuff like that. But sometimes there's a bit of machismo there of like never using a loop when actually a loop is an easier to understand way of doing it, and it ends up with the same machine code in the end.
The nice thing about algorithms like this, right, is that they have names.
Yes. I mean, the fact that there's a named algorithm for this is great. I agree.
Yeah. And so as soon as you see a take while or a drop or do you call it map in Rust? A map.
Yeah.
Then you know what's going on and you don't have to, or you see a take while and then, okay, the next thing is the condition, right?
Yeah.
If I have a loop, I have to kind of compile a loop in my head every time.
Yeah.
And that is the benefit of the named algorithms. If you end up with a thing that's going, okay, iter next, take while, map something, filter something, that you maybe want to put some intermediates in there, right?
Yeah. I think generally where I bail out is when I'm in a closure inside some map or something like that, and then I start doing more chaining inside the closure. At that point, I'm like, I'm obfuscating things. I can no longer read my code. But
I would agree. But I think, here, we've got...
I mean, that's beautiful.
We know that's our iterator. We're doing that, and then we're applying a test, or we're collecting it. There's no filters or any of these. They're all like, bum, bum, bum. Okay, take while. We haven't got to the end. Pop it in a string. Lovely.
Yeah, it's lovely. It's lovely.
So that's... I think it's really... I'm really quite pleased with this.
Yeah. And if you ignore the tests, it's quite a low line number count as well, isn't it?
Yeah, it is... we're down to there. So 177, it says there, which is, I don't know, but maybe it is. It's.
I mean, the original's pretty good.
But we've necessarily got more stuff.
We've named a lot of
types because we have to. It does make it clearer to name this stuff. Yes. We've just got more scaffolding around naming the Lexer because we've got the pubstruct here. We've got how we construct it, and then we've got where we implement the iterator trait is an extra bit. So there is just more scaffolding.
Yeah.
But I think it's still pretty tight.
Yes. Yes. And I personally, if I was coming to work on this code base, if I had to choose between the Python and the Rust, I'd definitely choose the Rust. I'd be happy to read twice as many lines of code.
I do think it's clearer. But one of the things that surprised me, having arrived here, because there were loops that I'd written, which I then replaced and what have you, is that the the two big selling points of Rust are memory safe, which is good, but actually, honestly, not a concern for most of us most of the time.
Yeah, well, there's lots of other languages that don't have segfaults, right?
Right. Well, it's just that actually we're writing things that are internal.
Okay,
I've got
so
a
you
lot
don't mind crashes anyway. Fine. Yeah. Okay.
Well, they run in ephemeral Nomad containers, so they spring up. They run for half an hour,
right.
and then we kill them.
Right.
If and they're GC'd, and the GC is not great, right? So it's like, but no, not that. Anyway, no, it's a separate thing. And then the other one is that it's a systems language. You can write all those gnarly systemy things that you're forced to write in C. And that carries with it an expectation about what the code's going to look like.
Right.
And it doesn't look like this.
Yeah, because that's interesting you would name those two things, because to me, the key advantage of Rust is actually, for me, something that it shares with C++, which is that it has an expressive type system. And I actually think it has a more expressive type system than C++. But before I got into Rust, C++ was the closest that I knew, because although I knew Haskell, I couldn't actually produce code in Haskell.
Yeah.
So yeah, the fact that I can express my types in a way that constrains the compiler to enforce the rules of how things work in a way that fits my brain, that's what makes me happy about Rust.
So certainly the things I found very easy. Where am I? I've got my little utility function down here somewhere to make a take. Here we are. So I've got constraints on my generic types, and I just wrote them, and they worked.
Yeah, and C++ took quite a long time to get something like that, right?
Yes, and I'm not sure I know what the syntax is off the top of my head. Right. Whereas this, I just I just stuck it in there, and then it worked.
Yeah, it's
and
pretty
the errors that I got while I was getting there were like, oh, you just need to do this thing. And you go, oh, okay.
Yeah. I love the compiler errors are amazing. Yeah, I love them. And I think also the power. There's a lot of power there as well in terms of these into blah traits that you can say, instead of saying my thing is a string, you can say it can be converted to a string. Like you've got this two strings.
Yes.
And that is a huge amount of power in that. Makes it very flexible.
So at the moment, then I'm assuming the str is basically like a character array, like we said, essentially, and the string is like a heap allocated dynamic thing.
Yes. Right? So a string is very much like a vector. It's some memory that you own that might get moved because it might grow. But at any one time, you know that its bytes are going to be a contiguous array of UTF-8 bytes.
Right.
But they might move around, and you own them, so you will tidy them up when this string gets deleted.
Yes. Okay. So that's as far as I've got with my understanding of, I don't know, I suppose stack and heap allocation, right? That's as far as I've got. So I've got my lovely Lexer.
This is super impressive. I
Thank
think
you.
it's excellent.
I had a lot of fun doing that. I had a lot of fun, and now I'm into the parser, which is rather more difficult.
Right. So now we're going to write some code, and I might possibly put like a video. I might split the video.
Yes, because I'm aware that I've really rambled on.
No. That was really fun stuff. But now we're going to write some code, so it's going to change. We're going to change tone.
Okay.